Hello, I've got the answers to the photoelectron spectroscopy homework. It's a worksheet. Question 1 was talking about photoelectron spectroscopy graphs and asked what determines the position and the height or the intensity of each peak in the photoelectron spectrum. The position, which is the x-axis, is determined by the energy of the sublevel. So the x-axis is the amount of energy to remove the electron, or the binding energy, the ionization energy. So the position on the x-axis is due to the energy of the electrons. And then the intensity of the peak is how many electrons have that much energy. So in other words, how many electrons are in a particular energy level or sublevel. Question 2. Why is the distance of the energy level from the nucleus important in determining the corresponding peak position in the photoelectron spectrum? Well, Coulomb's law tells us if an electron is farther from the nucleus, which is where the positive charge is in the nucleus, then the attraction will be less and the binding energy will be less. And so the peaks that have lower binding energy, lower energy on the x-axis, those are the peaks that are farther from the nucleus. The ones with the higher binding energy are the ones that are closer to the nucleus. Okay, number 3, we have this particular spectrum. If you add up the electrons, A asks what element is the spectrum below 4. I say it is aluminum because the intensities add up to 13 electrons. And aluminum is the atom with 13 electrons. So the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p1, which corresponds to the peaks, the 5 peaks that are in the spectrum. Number 4, identify if either of the following statements is correct. If yes, why? If not, why not? Well, first off, this first statement, the photoelectron spectrum of Mg plus 2 is expected to be identical to the photoelectron spectrum of neon. Well, Mg plus 2 and neon both have 10 electrons. They are isoelectronic. So I would say I would expect them to have the same number of electrons in their spectrum. I would expect them to have the same peaks in the same order in their spectrum. But I would also expect the intensities of the peaks to be the same. But I would expect the energies to be different. The binding energy will be greater for the magnesium plus 2 spectrum than for neon. So they'll have all the same peaks and they'll all look the same, except they'll be in different places on the x-axis. And that is because magnesium plus 2 has 2 more protons. Stronger nuclear charge to pull the electrons in means more energy to remove it. So all of the peaks from Mg plus 2, which will be the same peaks neon has, but they'll be at different places, they'll be at higher binding energies. Now the second statement was the photoelectron spectrum of chlorine 35, which is an isotope of chlorine, is identical to the photoelectron spectrum of chlorine 37, which is another isotope of chlorine. 2 isotopes of chlorine should have the same photoelectron spectrum because all they have different is the number of neutrons. And neutrons have no bearing on the attraction of the nucleus for electrons. And so chemically and electronically, chlorine 35 and chlorine 37 should be identical. Okay, and then on the next page, question 5 shows us a spectrum and tells us that it is the spectrum of potassium. And it says, explain why the peak at 0.42 millijoules per mole or megajoules per mole is identified as being in the 4th energy level. So the 0.42 peak is this little tiny one that has the lowest binding energy of all of them. And since it has the least amount of binding energy, it would be the one that's closest or to the outside of the atom or farthest from the nucleus. And also it has the least number of electrons. In fact, the peak corresponds to having only 1 electron in it. And so that means it would be the 4s1 in potassium. So the other peaks are the 1s2, 2s2, 2p6, 3s2, and 3p6. And then following that, you would have the 4s1. And that would be the peak at 0.42 megajoules per mole. Okay, and then we have these three spectra for nitrogen, oxygen, and fluorine, respectively. The general trend across the period is that for nitrogen, oxygen, and fluorine, you expect all the various peaks to have higher binding energy, higher ionization energies. And that is true for the 1s electrons, 39.6 for nitrogen, 52.6 for oxygen, 67.2 for fluorine. It's also true for the 2s electrons, 2.45 for nitrogen, 3.04 for oxygen, 3.88 for fluorine. However, for the 2p electrons, it's 1.40 for nitrogen, 1.31 for oxygen, 1.68 for fluorine. So for the first ionization energy, which would be a taking electron out of the 2p, oxygen's ionization energy is actually lower. Even though the trend left to right is ionization energy goes up, oxygen is lower than nitrogen. It's an exception to the rule. And that is due to oxygen being the first element in that 2p sublevel to double up and put 2 electrons spinning oppositely in the p sublevel. And so the extra repulsion coming from doubling up in the p sublevel actually creates an exception to the rule that left to right ionization energy increases.